graphs with the time asymmetry, spectral optimization, and spectral statistics.
Thank you, Sasha. Okay, first of all, thank the organizers for inviting me to this semester, to this nice place. It's always a great pleasure to be here. And as Sasha said, I will speak about quantum graphs, which is the topic which was here already. So I mean, no big introduction, but still, in a nutshell, few basic facts. So discovered by Linus Pauling about a century ago, and then happily forgotten for half a century. And it has a revival in 1980s, and since then it's a hot topic. Now on a metric graph you can put various equations, Schrödinger, Dirac. From the physics point of view, they are used as model of various nanostructures, things like that. And you can put there other operators. You have other applications. Nowadays, the literature about them, I mean the monographical literature is rich enough already, so there are at least 4 big books from which one can learn the basic facts. Now, so that was the graphs were mentioned, but in contrast what Delio said on Wednesday, there is one thing I have to stress, because what will be important here will be the vertex couplings. So if I have a Laplacian on a graph, a second order operator, in order to make it self-adjoint, I need to impose conditions at the vertices of the graph. And since it is a second order, so the conditions should involve the values and the values of the derivatives. And the most general condition of the type is a linear relation like that, with a matrix coefficient A and B. And in order to have it self-adjoint, then the coefficients should satisfy two requirements. First of all, if you arrange two n by n matrices into a matrix n by 2n, it should have a maximum rank. And the second one is that this combination should be Hermitian. Now, this is usually ascribed to Kostrikhin and Schrader, but as Barry Simon likes to say, in Soviet Union they knew everything 1 generation earlier. So you can look at the paper by Rofe Beckett of 30 years before, where you have exactly the same condition, even with the same notation. But well, the drawback of the condition is, of course, that it is not unique. If you multiply it from the left by a regular matrix, you get another pair. So there are various ways how to make it unique. The one I will use it to choose the A and B in the form like that, U minus I and I, U plus I, where U is an n by n unitary matrix. There is one more parameter here, but it does not multiply the number of extensions. It just fixes the length scale, and usually I put it equal to 1. Okay, now there are various simple examples, and these examples, from my point of view, they are invariant with respect to the time reversal. One standard is the delta coupling, that is, the functions are continuous at the vertex, and the sum of the derivatives is proportional to this common value. It's the only class in which the wave functions are continuous at the vertex. If this coefficient here is 0, that's the Neumann-Kirchhoff of which Delio spoke. But certainly there are many more. And in order to look, I will explain why I am interested in a violation of time reversal in a minute. In order to have an example, let's look how the S matrix, on-shell S matrix corresponding to the U from the coupling condition looks like. It's this simple rational function. And the example I will be most concerned is very simple matrix, which in elements looks like that, which is now, why I choose that? Because if you take k equal 1 or k equal 1 or L, then the S matrix at this momentum is just the matrix U. So I choose a situation where a particle coming on the first edge leaves on the second edge, from the second to the third, something which obviously violates the invariance. If I write it in components, the conditions now look like that. And it is clear that it is not invariant with respect to complex conjugation, which represents the time reversal. Now, I promised to say why I'm interested in these things. Now, the motivation came with yeah.
What is this matrix? What does it correspond?
That's the scattering matrix, scattering operator reduced to energy, what the physicists call on-shell scattering matrix. That is, if you put say in other words, if you put a wave of with momentum k and let it scatter, so it tells you the.
Where do you put it? I'm just trying. You're talking about one single vertex at the moment.
At the moment, I'm trying to describe one single vertex, but then I.
So the scattering happens, in the neighborhood of this matrix.
Well, it is since it's a one-mode thing. Yeah, the asymptotic region starts immediately when you leave the vertex.
Yes, I understand that.
Yeah.
It might not. You don't even probably have to have this asymptotic, even to go to infinity for anything, because you probably compare the.
Of course, yeah.
On the other. On the other edges.
That's what I'm saying. I mean, the scattering is just limited to the vertex itself. Once you leave it, nothing happens. It's asymptotic from the first moment you leave. Yeah. Okay. Okay. So now our physicist friends try to model the anomalous Hall effect. Everybody knows that quantum Hall effect is a great thing. I mean, 2 Nobel Prizes. And but its mechanism is well understood. But there is anomalous Hall effect, the same thing, transverse conductivity, but without the magnetic field. And there the mechanism is much less clear. And there was a model in which they use a graph such a lattice in order to compute the conductivity. But the model has a flaw. Because they used the delta coupling, and in order to get a non-trivial result, they had to impose the preferred orientation of the loops, which is something you cannot justify from the first principles. You cannot tell the electron on a line go left or go right, but you can violate the invariance in the vertex. So that's why we got interested into sync and started studying the vertex coupling of that type. Now, asking which conditions are invariant with respect to time reversal, of course, the natural answer is if the matrix coefficients are real valued. But then, of course, you want to know how it looks like because the A and B is not unique. So how it looks in terms of the matrix U, which is a unique characterization. Now, from a bit more general point of view, the symmetry. If you have such a condition, so Laplacian on a graph in the vicinity of the vertex, and now if you want to symmetry represented by some map theta from Cn to Cn, because nothing non-trivial happens on the edges. All the non-trivial things are at the vertices. So the matrix U should satisfy this condition. Now, in connection to the time reversal, which is in the absence of the internal degrees of freedom, just complex conjugation. Since we know that the matrix U is unitary, then you easily find that the corresponding matrix theta representing the time reversal is just transposition. So the invariance with respect to time reversal means the invariance of U with respect to transposition. And as a side, because I mean now there is a popular thing to ask about PT symmetry. And people construct non-self-adjoint graphs with PT symmetry. Whether you can have a self-adjoint graph with PT symmetry. So if you want to that, then of course the parity should act the same way, transposition. Now, of course, while time reversal you can do without any reference to the embedding into a Euclidean space. In case of parity, you need to think about that. And for simplicity, I will restrict myself to planar graphs. Now, in general, it's difficult, but there is a class of matrices for which it works. And let me recall what the circulant matrices are. These are those which have same values on each diagonal, and they are cyclic in the anti-diagonal thing. That's an interesting class, which has a property that first of all, all of them have the same system of eigenvectors. They are of this form where omega is just the nth root, complex root of unity, and they are all diagonalized by the discrete Fourier transformation. And not surprisingly, there is a relation between their eigenvalues and the entries of the matrix, these linear relations. So now, if you want to ask about the form of the matrix theta, then you realize that you can always diagonalize a unitary matrix, and the unitary that is a diagonal matrix is invariant with respect to transposition. So since you know the matrix, which in this case diagonalizes, you easily find that this matrix theta is now this combination of the diagonalizing matrix of the discrete Fourier transform. And if you compute that, you will find this matrix here. So if you look at that, one edge stays, and two pairwise they switch roles, which is a reasonable way of regarding it as a parity. Now, this tells you that among all the circulant vertex coupling, roughly 1/2 has a non-trivial PT symmetry, even if they are self-adjoint, and the other has P and T symmetry separately. Okay, but now let me return to the basic example. Let's consider the simplest graph, that is star and infinite star and half lines connecting in such a vertex. So the essential spectrum, of course, is the positive half line, but there is always a negative spectrum, unless, of course, you have the trivial case, just line. So if you compute, it's easy to take the ansatz, exponential ansatz, put in the boundary condition, and find that there are always negative eigenvalues, especially in the simplest cases when 3 or 4, you have just one eigenvalue, which is respectively equal to -3 or -1. As for the scattering, now the formula we had before, and if you look at that formally, it seems that it has a limit which is a multiple of a unit matrix as k goes to 0 and to infinity. We will be particularly interested in the high energy asymptotic ski. But of course, the argumentative formula, a counterexample, is a scattering matrix for Kirchhoff coupling, which is independent of energy, and it is not a multiple of unit matrix. Now, in order to understand what's happening here, let's compute the S matrix entries. That's this horrible formula where eta is just this combination of 1 minus k over 1 plus k. Well, it will tell you like that, not much. But let's look at the simplest examples, 3 and 4. And if you take the limit where k goes to the energy goes to infinity, which means that eta goes to -1, you see that there is a big difference between the two. Namely, if n is 3, or in fact any odd number, then the limit is indeed a multiple of the unit matrix. That is, the edges asymptotically decouple. While if you have 4 and in fact or even number, the limit is non-trivial. And the reason is not that much the parity. The fact that the matrix U has or has not -1 as its eigenvalue, because this is the thing which spoils the formal limit. Okay, now so now this coupling was studied. We studied it in many cases of graphs which are infinite periodic lattices. I will not mention that. I will mention just one example which will play a role in the following. Namely, if you take a square lattice graph with this coupling, this violating the time reversal invariance, the R coupling as I call it, and you put it into a magnetic field. Was it Kirchhoff coupling, say, you would see that the spectrum as the function of the flux of the through the unit cell gives you the famous Hofstadter butterfly. But now you have two mechanisms which both violate the time reversal magnetic field and this coupling, and they compete with each other. And if you plot the spectrum, you see that the coupling, the vertex coupling, influences significantly the shape of the spectrum at low energies, but asymptotically at high energies, the Hofstadter is restored. I mean, a part of these things which need to be discussed separately, but the main thing is that the influence of the coupling is important at low energies only. Okay, now, but I will now, the basic subject of my talk are finite graph. In a finite graphs, you see also the difference between the graphs of the vertices, different parity. As an example, you can take graphs which correspond to edges of these Platonic solids. If you look at their discrete spectrum, but it differs from one to another. Namely, these four have the spectrum which asymptotically the eigenvalues or square root of eigenvalues approach the integer multiples of pi, which is understandable because I mean the degrees of the edges are 3, 3, and 5 odd numbers. So asymptotically, the edges are decoupled, and you get the values which correspond to just to intervals. While the octahedron has two additional series, which are given explicitly here, and for comparison, if you put a delta coupling, say, you see no such difference. Anyhow, but there are effects which go beyond the asymptotics, and the first one is, that's the first main topic of my talk. Namely, you ask about optimization. You have a finite graph with this coupling, and you ask about the topology which optimizes the eigenvalues. Okay, so now we start with optimizes, maximizes the ground state, several other inequalities you will see. Yeah. Now, so we start with the simplest case. You take again a star, now a finite star with generally different lengths, and one vertex in which you impose the R coupling. That's the one which I had before. And know that, for example, if you sum this condition, you find that the functions satisfy a part of the Kirchhoff condition. Sum of the derivative is 0. But of course, they are not. The functions are not continuous. The domain would be Sobolev, but without the continuity at the vertices. Now, the first thing is that we will need a quadratic form or sesquilinear form, which is associated with this operator. So it is here. You see that there is, not surprisingly, there is a kinetic part. Then there is a vertex part, which is coming just from integration by parts. But there is a difference. Again, the parity plays a role, because there is a difference in the domain. If the number of edges is odd, then the domain is just the first Sobolev. As I said, the tilde means that without the continuity, just Sobolev on each edge separately. And while in the case of an even thing, you have the same thing, but you have an extra condition, such that the signed sum of the values must vanish. Now it also tells you, for example, that the negative spectrum is non-empty, but we all already know it, so I will skip that. And now let us start playing with the graph. So the first thing is transplantation. You take such a star, and you start playing the game. You put a part of an edge and put it to another edge. Of course, the total length of the edges is conserved, and let's look what it'll make to the eigenvalues, especially to the ground state. So if I do that, and I make such a transplantation in the way which increases the disbalance of the graph, yeah, the relation between the edges. Then the ground state is going down. Well, in order to do that, you just play with the quadratic form. That is, you take the ansatz for the solution, which, because I have not said, I suppose that my star, it's a finite star, and a Neumann condition at the edges. So then the ansatz is just hyperbolic cosine, and the vertex condition require that I have this condition here. And now I construct a trial function. I will, with the one which is shortened, I cut simply the function, and the one which is extended, I take the function which was there and I add a piece of the function from the first edge, like that. But I have, of course, to choose a coefficient in such a way that I join them smoothly. And now I compute the value of the quadratic form and find these inequalities. So the one after the transplantation satisfies this inequality here, where this is the eigenvalue, the ground state without the thing. And for the norms, I have this thing here. And since I know that the ground state is negative, it gives what is needed, that the transplantation pushed the ground state down. Okay, now I can now do this iteratively. If I have an unbalanced star, I can put pieces from one edge to another until finally I reach the equilateral graph. And if I use iteratively the result I just announced, I found that if the length, total length of the graph is preserved, that I have the inequality which says the ground state is not exceed the one with the equilateral graph. And that the inequality is saturated if and only if this gamma is gamma star. Now, in a similar way, I will not say much about the proof because it's all the play with the quadratic forms. So I can now compare graphs which still have the same total length.
You are not showing us the proof, but is it again based on the explicit calculations?
Yes.
That you're just writing out this?
Yes. Yeah, it's all constructing trial functions. So if I conserve the total lengths and compare equilateral graphs, so if this one has two extra edges, you have this inequality between the ground state. If I add just one edge, then I have this inequality if n is odd, and I have the opposite inequality when n is even. Furthermore, if I now proceed, I mean removing edges and doing in such a way that the length is preserved, I will finally find that the ground state of such a graph, star graph, is bounded from above by the graph or 3-star or 4-star, depending on the whether the original n was even or odd. Now the next thing. Now I start surgery, which is not just transplantation, not using only the flesh of the patient. Yeah. So I will add one edge rooted in the common vertex. And then if the n is even, then adding the edge will push will not push it up. Yeah, it's not sharp inequality. And the same will be true generally if n is odd. Again, that's the minimax. As I said, I will skip the proof. So I will, in such a way, I come to the conclusion that the even number edges, attaching the even number of edges to the graph will again push the eigenvalues and not only the ground state down. Using that, if I have an even number, n, then I can remove subsequently the pairs of edges until I found an equal 2. An equal 2 is one interval. You may say that it's two intervals, but the coupling I have is trivial for n equal 2. It's no coupling at all. So it gives me for even n these inequalities here. Just comparing with the eigenvalues of an interval. Of course, the thing which interests us most of all, that is lambda 1, is trivial here because we know that's negative, and you just see here that it is bounded up by positive numbers. Okay, so now. The enlarging the edges, I get now that as long as the case eigenvalue is negative, then I have this inequality here with the enlarged here. In particular, for the ground state, I have this thing here. And if the eigenvalue is non-negative, then I have this inequality for all k. Now, as a comment aside, I took a star with Neumann conditions. If I put instead Dirichlet endpoints, then I have the form is like that. The domain is again like that, with the added condition that the values of the function at the end, loose end of the edges is 0, and then I have the inequality I had before, but now for all the eigenvalues, that extending the length pushes the energy down, which in case of Dirichlet is of course trivial, coming from Dirichlet bracketing. Okay, but now that was just a preparatory stop. What I need now is to look beyond the star graph. I have an arbitrary finite graph, finite number of edges, and I want to know what happens with the spectrum, or how to optimize the spectrum in terms of the topology of the graph. So I need the spectral condition generally. So to write it, I write the A and B, which is just the matrix, which is U plus 1. In fact, I'm not consistent. B was I, U plus 1. Here, B in this notation is just U plus 1 without I, which will be there. But it is this matrix here. And now I have a big matrix A and big matrix U, just put them on diagonal of one great matrix. And in addition, of course, I need Neumann to Dirichlet, or if you want, a transfer matrix, which maps the solution from one vertex to another over an edge. And it is, of course, something like that. So if I put it now together, I will find that the spectral condition for such a graph is in this form. These are these big matrices. Here is the M, which is again the block diagonal matrix of these transfer matrices over edges, and these are the values at the vertices. So it's a system of linear equations, and its solution is just you look at the determinant of this matrix and ask whether it's 0. Actually, you may notice that in my in my conditions, the order of the edges around the vertex was important, but in the condition it is not. It does not show. It's just if you renumber them, the condition will be the same. Now, an important example. Now you take a graph which has a form of 8, just 2 loops, one vertex of degree 4. The lengths are in general different of these loops, L1 and L2. And for negative energies, again, the ansatz for the solution is hyperbolic cosine and hyperbolic sine, such a linear combination. And you put it into the spectral condition I showed you. And after a bit of computing, you find the secular equation, which looks like that. And now, you look, all these factors here are non-zero. So the only thing where you can get a negative eigenvalue is here. It is -1, and it is -1 independently on the length of the lobes. It also tells you that the second eigenvalue is 0 here. Now, so that's what I said. For the positive energies, you have the same thing. Now the condition would be like that. Now this would be non-zero, but the counterpart of this one is this, and this of course has solutions, and you also see that the solution, the eigenvalues scale with a simultaneous change of in general, such a graph is not generally scale invariant, but this part of the positive spectrum scales. In addition to this scaling, there may be other eigenvalues, but for example, when it's equilateral, then you explicitly see that the eigenvalues are just 2 pi n square. Now I need to revisit my toolbox. So 2 things. First of all, I need the quadratic form of the whole graph. It's just the sum of the forms of individual vertices. And the second thing, more important, is I will start playing with vertices. I mean, merging them or splitting them. I mean, here is a formal definition, but you know what I mean. I take 2 vertices and put them together, join all the edges from the 2 to one single vertex, or I cut it and produce from a single vertex 2 vertices. And now the technique to be used. So merging a vertex. So the merged graph is a merged vertex is again tilted, and the result is like that. If I merge 2 vertices in such a way that the sum of the degrees is odd, which means I merge even and odd vertex, then I get this inequality. The merging of the vertex pushes the case eigenvalue down. If I merge 2 even degree vertices, I get the same. But if I merge 2 odd degree vertices, I have the opposite inequality. Okay, so now we arrive at our first main result, which says that I take again a finite graph, and I, of course, will not consider trivial cases, an interval or a loop. I need that there is at least one vertex of degree at least 3. Now, if I do that, what I will do, first I take such a graph and look at the odd degree vertices, and I merge them, producing even degree vertices. In fact, I can merge all the vertices into one. Certainly the total degree is even because every edge has 2 endpoints. So that's the first step. And then I will proceed in the opposite way. I started splitting these vertices. But how I will do that? I will do that not to spoil any Eulerian path. That is, I split always an even degree vertex into pair or even degree vertices, never too odd. And I use the inequalities I have, and I proceed until finally I will arrive at the figure 8. And the figure 8, I know what the spectrum of the figure 8 is. So here is the result. I have, except of these trivial cases, that is cycle or a path graph, I have the first eigenvalue does not exceed -1. The second is non-positive, and for the odd eigenvalues, I have this thing which the inequality I had before, and well, first it has there is always a negative eigenvalue, and secondly, these inequalities cannot be improved. That's the optimal result. Okay, so that's the work now to give credits. That's the Jonathan Rohleder paper we wrote together and which is hanging for a year now as an online ready in Annales Henri Poincaré. Okay, so now let me switch the topic. Still I am with the coupling I described, but now something different. Yep.
Just to understand this better, when you say that it cannot be improved, does this mean that there is a graph where this inequality is attained?
The figure 8. The figure 8, yeah. That's it. Yeah, I said -1, and for the rest.
Any figure 8 graphs, regardless of the
Yes. Okay, so now a different topic, but still with the same vertex coupling. Now, as we all know, Kotos and Smilansky taught us that quantum graphs are a good tool to study quantum chaos. And in particular, we know that if the graph has there are no internal degrees of freedom, and there is no spin, let's say, and the graph has a sufficient connectivity. I will not go into what is sufficient connectivity, not a star graph, yeah. And then the claim is that basically everything falls into two universal classes. Gaussian orthogonal ensemble if the graph is time reversal invariant, and Gaussian unitary ensemble if it is non-invariant, and the non-invariance is typically connected with the presence of the magnetic field. Now, I'm using this coupling, this example of the coupling, to challenge this paradigm. But first, I should say what are the quantities we are going to...
Say, when you say we know, and at what level?
Well, that's what's...
Level?
It's generally accepted that, generally accepted, yeah. Yeah, what I'm going to show an example. Yes. I am going to give you an example that things are not that simple, yeah. So the quantities we consider, so it's the nearest neighbor spacing, which is like that. Everybody knows, and the 2-point correlation function, which is not a probability measure. There is no n square here. And it's Fourier transformation or up to this thing here, which is a form factor. And of course, as usual in quantum chaos, you have to unfold the spectrum to get. But here, unfortunately, it is trivial because we know that in graphs, the Weyl law is like that, even if the vertex coupling is non-trivial. So no unfolding is needed.
Sorry, when you say time reversal symmetry, it just means that the operator is real. Is that the same thing?
Okay. Yeah. Okay. So now, look what. So what?
The symmetry is not well defined. That's what he wants to say.
Yeah.
Okay. So now, these two pictures. They concern the spectral statistic of the following graph, which is an octahedron, and it's not regular octahedron. I mean, it's the edges are incommensurate. And here is the nearest neighbor distribution, and here is the form factor. Now, two surprises. This distribution, lo and behold, is not GUE, it's GOE. It's we know that the graph violates the time reversal. We constructed it like that, but it's still GOE. And second, this fits nicely into the GOE, again GOE formula for the form factor. But there is one disquieting thing. This peak at the tau equal 1/2. So what to do with them? So that's what I'm now reporting is a common paper with Rami Ban and his students Divya Goel and Avia Cohen. So the first, before coming to that, let me show that the effect is subtle. I will change slightly the graph or the coupling. Here I will take, instead of octahedron, I take a cube, again an incommensurate cube, and then I take an octahedron again. But now what I'm doing, in the first case, you get this distribution, Poissonian distribution, which is maybe not surprising because I know that the cube now has degree 3, so asymptotically the edges are decoupled. So at high energies, it's the same like the independent intervals. So this explains the Poissonian distribution. But here it's more subtle. I take the same octahedron as before, but now I change slightly the vertex coupling. Namely, instead of R, I multiply by this complex factor. And mu is, in this example, is something very small, 1/100. What I did, I told you that all depends on the presence or absence of -1 in the spectrum of U. Now, the U for the R coupling is 1 - 1 I minus I. Now I take the spectrum and rotate it slightly. And here is the result. The effect disappeared and I have the Poissonian distribution. Actually, you would expect whenever the mu is not multiple of pi/2, the same effect, just for the smaller mu is, you need more eigenvalues to compute. Here we had something like 80,000. Okay, so as I said, it's Poissonian. The first, let's ask why it's so that the nearest neighbor is GOE. The point is that my time reversal violation of time reversal invariance is dependent on energy. And in order to assess what the dependence would be, let me recall that was an invariance with respect to transposition. Now this property translates to the S matrix, so the natural quantity to characterize the violation would be the difference of the S matrix and the transposed S matrix, the norm of that. Of course, that's a bounded quantity by unitarity; it cannot exceed 2. So let's look how it looks like. The matrix M. You know I showed you the formula for the entries of the matrix S, and since it is difference of two circulant matrices, is again a circular matrix. So you can write the entries like that, and you have a prefactor here, and you have these quantities here. And now, since it is a circulant matrix, you can, knowing the entries, you can reconstruct the eigenvalues. They're here. And now, if you ask how it behaves as the energy goes to infinity, so you distinguish two parts. There is a prefactor here, and this norm of this coming from these eigenvalues. Now the prefactor is here. If you write it in terms of E, if you return to the momentum variable, you see that it depends again. The asymptotics is different for different parities. If M is even, it goes to 0 like that. If M is odd, and well, it is non-zero limit, and if m is odd, it goes to 0, like 1 over k. On the other hand, the eigenvalues look like that, and especially if I take if I close to infinite energy, that is eta is -1 plus delta, you see that again for even and odd there is a difference. Delta is here, but it is not here. So if you put that together, just two differences compensate each other. And the result is that the quantity we are interested in behaves at high energies as O of 1 over k. So the violation disappears.
To me, that indicates that you are looking at the wrong quantity because you have close pairs, eigenvalues. You haven't unfolded correctly.
No, the eigenvalues,
If you go back to that previous slide,
yeah,
you're saying that the k. Ah, no, sorry. So
No.
k is the.
yeah, yes, k is a label that yeah. Yes. So you have this thing here. Actually, even if k goes to 0, you have a 0 limit. In fact, you can compute it explicitly for 3 and 4, and you have this explicit formula. So you see that both these measures of they saturate. There is a value of k for which they equal to 2. But it happens at a different, here it is for k equal 1, here it is for k equals square root of 3. So now at the limit of high energy, the S matrix elements look like that, and that's very similar to the Kirchhoff coupling. Just the difference is this sign factor, that is, instead of Kirchhoff coupling, you have the matrix in which every second diagonal changes sign. So this explains, well, because I mean the asymptotic behavior is responsible for the distribution of the nearest neighbor. So the values at high energy is decisive, and since there the violation disappears, then no surprise that we got GOE. But now, how about yeah?
It's the general opinion. So if I have an operator that almost commutes with complex conjugation in the sense that the commutator is lower order, you would still expect GOE, right?
Okay, yeah, well, yes, okay, but first you have to know that what we, yeah. Okay, so now that's the second thing. What happens with the mysterious peak at the mysterious peak in the form factor? Now you can compute the thing from the eigenvalues directly, or you can take the secular equation of that time and compute the eigenphases of this big matrix U. 2 is the number of edges, and if you look into the literature, you find that at discrete values of the parameter tau, the form factor looks like that, as Grisha Berkolaiko teaches us. And moreover, that you can re-express it as the sum through the sum over periodic orbits. In this formula, so E, as I said, is the number of edges. A are the probability of passing through a vertex. L are the lengths of the pass, and if the periodic pass is repeating, there is a repetition factor here. But in fact, since it's a quite complicated thing, usually the people start with the diagonal approximation. They take just the pass, the same pass, up to the reverse orientation. So that's what we will do. Now, here, let me show you that. You can have the GOE in other graphs. So here we computed for comparison the form factor from for the complete graphs K7 and K9, like that. And we computed it in two ways, through eigenvalues, that the red curve, through eigenphase is it's the blue curve, and you see that they are nicely sitting on the GOE formula, which is given here. Okay, now what about this mysterious peak? So here it is again. And you see that again, we computed it through eigenvalues, eigenphases, and in both cases the peak is there. But to our surprise, I mean, people computed the thing for Kirchhoff coupling, and the peak was there, but nobody noticed. So what is that? So let's try to use the diagonal approximation of the formula. In our case, E is 12 and tau is 1/2, so it is just 12. So and of course that's a rather complicated thing, because there are many periodic. We concentrate on one particle class, which are Eulerian paths.
This is still in the diagonal approximation.
Yes. So Eulerian paths, and for an Eulerian path, since the S matrix is up to the same in every vertex, it just gives just the power of this quantity here. And in order to get the contribution from the Eulerian path, you need to know how many Eulerian paths you have. And that's a rather demanding thing, because it's a complicated combinatorial problem and non-polynomial. So we had to invent two ways how to compute this number. But if you do that, you will find that for our octahedron, there is 744 Eulerian paths. And if you then compute the contribution, it's something like 0.2. And if you look back into the diagram, you see that the value of the GOE is 0.65, and the value we computed numerically at the peak with a small error is like that, which means that the Eulerian paths explain more than 70% of this difference. Why Eulerian paths? Actually, because they are a very small subset in the family of all periodic paths. The point is that they are the only one which have purely constructive interference. All the contributions over the paths are positive. With the other paths, you change signs and you can have destructive interference. So the whole number of paths is something like 1.5 million. So that's less than 1,000, but still it explains, let's say, more than 2/3 of the effect. This is not the same thing, not the only exact. Sorry? Well, that's, I mean, you have 1.5 million paths, so I mean, there is, I mean, we do not claim to explain that completely. We just say that we have identified a factor which contributes most significant. No.
Factor that doesn't cancel out this particular one.
Yes.
Yeah, it's a conspiracy. At this age, it's
Sure. So we look into other graphs. So for example, K5 and the Eulerian contribution is 0.3, and you see that here is the numerical computation for K5, and you see that there is a peak even bigger, and there is another peak. And if you do the same for the Kirchhoff coupling, you see that there are even more peaks there. Okay, so that's well. Now again, this is a relatively large number comparing to this, not explaining everything, but still. On the other hand, it's not always the case. For example, if you have non-Eulerian graphs, you lack such a mechanism, and then you would not expect. And in the examples you look what people computed, you never saw such peaks. But also, there may be absent even in graphs which have Eulerian paths. If you go back to the K7 and K9, yeah, you see that there is some numerical nonsense around 0, but otherwise there is no peak on the graph. And you may ask about the contribution of Euler. So in case of K7, you have 21 edges. So you have this number, or the number of the Eulerian paths, goes to millions. But then the number of all paths grows much faster. So the contribution is still there, but it's that small. And if you go to K9, it's even. So here is the number of Eulerian paths, and the contribution is of order of 10 to minus 7. So anyhow, so it is not maybe the full explanation, but it's a hint what's going on. And the conclusion might be that the time reversal asymmetry can produce this effect due to the smallness of the graph and its topology. But I think my time is over. So what remains to say? Thank you for your attention.
Thank you very much. Questions, please.
How do you compute the number of Eulerian paths?
Sorry?
How do you get these numbers?
Well, that was quite a lot of work.
But you're sure that this is actually correct? Or is
We devise two procedures how to compute them, which led to the same result.
Well, you should find the third procedure.
And we discovered the missing 1/3, right?
Actually, I mean, the GOE thing, it was simple, but this took us months of effort. Yeah.
More questions, please.
I just, a couple of weeks ago, we heard, one of us heard here a lecture by Eugene Bogomolny, who was playing a similar game for hyperbolic surfaces. And there, for generic surface, you're supposed to get GOE, but for some surfaces, you seem to get Poisson, like in your case. And part of the explanation had to do with the existence of systematic degeneracies in the length spectrum, which is somewhat similar to Eulerian paths in spirit, and that has a similar effect. But I never saw this peak at an form factor discrete point. That seems to be an out.
Well, our first reaction, okay, it's numerics, but then we did it different ways, and it was still there. Yeah, and then to our surprise, we recovered it for Kirchhoff coupling, and we found that other people did that too, but they did not pay attention.
Because it violated the orthodoxies.
Yes.
But large then it disappears.
Yeah. So yeah, that's all the effect of small graphs. Yeah, for example, you saw the K7 and K9. That's all lost. I mean, the effects are too small to influence anything.
For small spin graphs that you can see, quantum spins, there are such big steps, but I never imagined that.
Yeah. I mean, it's a bit tangential to the last part of the talk, but if you try to understand more the quadratic form, do you know if there is anything close to a diamagnetic inequality for this system? So if you take the parabolic equation driven by the spreading operator.
I understand a good question, but I have not thought about that. Yeah.
What happens in the loop? I mean, it was very fast. So if you have this figure 8 graph,
Yeah.
and you say the eigenvalues are the same for any length of the. So if you let one of them go to 0, so you have a loop what kind of strange boundary conditions or periodicity conditions?
Now, what do you do with the loop? Yeah, you will split it, or
It is that, so basically, it should be the limiting conditions if one of the two halves goes to zero. So basically,
well, these things are very subtle in graphs. That reminds me what we once did with Brian, who with Sasha observed the fact that the number of resonances violates the Weyl law if you have Kirchhoff and balancing. And the first idea was to look what happens with if you have the vertices which approach each other. But it was not so. It was there was a symmetry behind, because there somehow you split off the symmetric part, which discarded a part of the external edge. So effectively the volume of the volume. This is not the case here, but just I mean to say that these things in moving, splitting or merging graphs may be quite simple. Quite involved, even in simple case. Yeah, that's what I would say.
More questions?
And how, again, sorry about this peak again, how is it manifested in the level spacing distribution? Do you know?
What the? No. Well,
Maybe there should be some signature also there.
No.
They didn't see it. You saw the pictures. The form factor is very bad numerically. Level spacing is not smooth. Yeah.
More questions? Thank you very much again.